Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So good afternoon. Our speaker today is Dr. Anthony Arndt from the University of Alaska Fairbanks Geophysical Institute, and he is a career glaciologist who will be addressing us today on his work here at Microsoft Research as a visiting researcher, working with Azure and with his modeling framework. So with that, Anthony.
Well, thanks very much, Rob, and it's really a pleasure to be here today to talk to you about the work that we're doing. I want to just quickly acknowledge the invitation from Rob to come here and work as a visiting researcher. This has been a really incredible opportunity for me to work with Microsoft Resources and really apply it to the science that we're developing at the University of Alaska Fairbanks. And also really grateful for Microsoft Azure for Research grant, which is supporting the Azure Cloud resources that will be the basis of what I'll be showing you today. And a lot of this research is supported by a wide range of funding agencies, most of which are shown here. A lot of collaborators, students, and technicians, too many to list, but I want to just recognize that this research is a very collaborative effort, and it comes from a lot of different folks at multiple agencies. So today I want to cover a few different topics that are summarized here. The first is just to give you a brief overview of the scientific problems that we're addressing in our research and a summary of the different kinds of data sets. And I want you to get a sense of the sort of complexity of these different data sets in space and time and how this calls for a kind of different computational infrastructure than we've had in the past. I want to talk about the sort of methods that we've been developing in Fairbanks over the past couple of years, sort of our academic approach to these problems and the infrastructure that we've built around that. And then really some of these incredible tools that I've learned just in the past couple of months here at MSR that are really broadening those tools and allowing us to accomplish really integrative and collaborative science, which is the goal of all of our efforts here. So let's just jump into a bit of the science just to give you a bit of a flavor of the kinds of things we're looking at. We're studying the Gulf of Alaska system. This is a large band of glaciers and ice caps that surround the Gulf of Alaska. And this is some of the largest ice areas outside of the Greenland and Antarctic ice sheets. And the reason we get so much ice in this area is that there are some very large mountain ranges. There's 7 different mountain ranges in Alaska. And they act as barriers to these massive storms that come in off the Gulf and deposit large amounts of precipitation in the form of snow. And so you get upwards of 6 or 7 meters some years in some of these high mountain areas that create the formation of glaciers that then flow down to the ocean and discharge that ice into the ocean. So when you have all of this ice and snow close to a coastal marine environment, there are a lot of complex interactions that we have to think about. And one of the biggest things that we're concerned with is the fact that there's a vast amount of fresh water stored in these glaciers that as the climate is changing, this is being released into the oceans, and this is a major source of global sea level rise. Alaska contributes somewhere around 7% to the global signal of sea level rise, which is very high considering how much ice is there relative to the ice sheets. Furthermore, we have to think about all this extra fresh water getting into streams and lakes and out into the coastal fjord areas as that fresh water, which has a different chemical and temperature signature than the surrounding waters, enters these areas. It will have impacts on things like the ability of salmon to spawn, the kinds of terrestrial succession that occurs, and then the overall ecology of these fjord areas will really change rapidly as the climate varies and we get more and more of this water getting into these fjord environments. And we get different salinity and temperature of these coastal areas that causes changes in the coastal current as you get further out into the ocean. So what we have here is really interdisciplinary and complex data sets for which we need a computational infrastructure that allows us to do collaborative and cross-disciplinary research. a little bit more about the region that we're studying. This is in black, the Gulf of Alaska watershed. It has about 27,000 glaciers, somewhere around 87,000 square kilometers. That's about 4% of the area of the state of Alaska. The annual discharge from this area is somewhere in the order of the discharge of the Mississippi River. So very high fluxes of water passing through this area every year. And we want to determine how this is changing over time. So I'm going to take you through just a few of the data sets that we work with. And again, I want you to think about the complexity of these data sets and how they vary in terms of whether they're vector data or raster data, and how we can put together an infrastructure to handle all this information. The first here is just basic inventory data, which is where are the glaciers located. So these are really high density vector polygons that tell us the location of ice in this particular slide at 2 different times, with the yellow being areas where the ice has retreated since the 1950s, and red being areas where there's been a bit of advance. So we need this basic information before we can run any of our models and do any simulations. We have point and line data that's, for example, collected when we just put a ground penetrating radar underneath a helicopter, and we fly along and we use that to determine the travel time and the distance then to the interface between the snow and the ice. That tells us the depth of the snowpack for that particular year. And there's an example of us flying on a glacier near the Cordova region, taking these measurements. So high density of point observations, and it gives us traces like this, from which we can determine the layering of the snowpack and pick out that surface where we think the summer surface is from the previous year, and determine how much snow is there. And then that is used to determine the fresh water available for that particular season. Go ahead.
And when you fly over, how do you get anything underneath, the picture of anything underneath the surface?
It's a 500 megahertz radar, and it's basically, it penetrates through the snow, and then wherever you have a discontinuity, where there's ice, it'll show up like that. This is actually up in the higher accumulation area where we get multiple layers. It's called the fern zone. So we have to carefully trace that line upwards. There's tracing algorithms that help us do that as well. And then time series information from things like these high altitude weather stations. Alaska is very data poor in the high mountain regions. Most weather stations that we use to run our models are located down near towns where people live. So we install these stations, and then we get often real-time satellite telemetry feeds of temperature, precipitation, and so on. And that is another form of data that we're using in our analysis. And then finally, a lot of remote sensing information. In this particular case, we're looking at data from what's called the Gravity Recovery and Climate Experiment. And this is a really fascinating mission. It's 2 satellites, and we're measuring the intersatellite range, which tells us the orbital influence of gravity on the orbits of these satellites. And from that, we can determine temporal variations in the Earth's gravity. Here's a map of the overall net loss of mass from different regions around the globe, and you can see that really maps into where we are seeing massive amounts of glacier ice loss. And this is the time series for Alaska. So you see the overall trend of mass change, and then the seasonal cycle as well, from which we can determine that runoff component. So again, Alaska is somewhere around 7% of the sea level signal.
What is the mass balance? Is the remaining ice?
That's the net change in ice over a year. So 65 gigatons of water is leaving that storage, the ice, and going into the ocean.
So why is the net change reducing by the year?
Why is it?
It's going.
Oh,
There is lesser water that's being released in 2011 than 2003. Is that?
Oh, this is the cumulative mass. So we just start at an arbitrary 0. We're not actually measuring the actual mass of the glacier. We're saying relative to where it was at 2003, this is how much mass it has, a cumulative mass change, basically. So at summertime, it's losing mass. Wintertime, it gains some mass. And then because that is trending downwards, the net change of storage is around this value here.
And when that gets down and flattens out, That means the ice is all gone, and now you know how much ice there was in the ocean to begin with.
Yeah, that's true.
So what is the highest contributor to global sea rise? Is it the Antarctic thing, or is it the Greenland?
Greenland right now is the highest, and what's happening here is not only just the melting of the ice, but a big component of the loss there is the fact that there's this calving of breaking off of ice into the ocean. We call it dynamic mass losses. And that's linked to the fact that the oceans are warming up and kind of eroding away at the ice, where the ice is meeting the ocean, and then you get potentially very catastrophic losses of mass in those areas.
So what percentage does Greenland get credit for?
I think it's around 25-30% or so. I'd have to look that up, though, yeah. Okay, so our goal is to kind of model this process as much as we can, to reconstruct past conditions, learn about the system, and also we want to be able to run future forecast models, say how, is the ice going to disappear in 100 years, these kinds of things. So there's a lot of ways to do this. Yeah, go ahead.
Sorry, just a question on the previous thing.
Sure.
Yeah. So this is a fairly narrow set of latitudes in which, pretty much most of the melting is happening and stuff. And why is it that the other latitudes are not affected that much in terms of the ice melting? Like Antarctica spans, goes around, and so
right.
does the Arctic, right? Like Russia and Siberia and so.
Oh, so I've cut this map off a little bit, but you're saying why is the loss focused on these?
Why is the loss focused most on these three? As opposed to like other latitudes.
Right, okay. It's mainly this.
Longitudes, yeah.
Oh, okay, I understand. Yeah. So the biggest players are Patagonia, Alaska, Canadian Arctic, as far as the non-ice sheet areas. Also the Himalayas, but it's off the map. I just cut it off, but it's not as big a signal. There's not as much, not quite as much ice there to begin with, and also these areas are more susceptible because, like I was saying earlier, they're close to the ocean. They're more sensitive to changes in climate because of higher precipitation rates, and they have ice that actually goes into the ocean, and they're sensitive to these dynamic losses as well. Yeah, and then really there's just not as much ice at mid-latitudes.
Can I interject also? You mentioned Siberia, for example. Siberia is this vast plains, but it's not like big, huge reservoirs and glaciers as much as it is just frozen ground.
So the main thing is it just frozen ground, or is it meeting the water? Is that the?
I think that what Anthony's saying is that when you have accumulated ice in glaciers, big, huge masses of ice that are facing into the ocean and they're warm, that's what's happening in Alaska. So you have this mechanism in place for transport of water into the ocean. Whereas in Siberia, my understanding is you don't have these masses of ice. So there's other things going on there that are related to climate change, but not so much water transported to the ocean.
This is the net loss over, this is the trend in mass, right? So that's this sort of red line mapped onto here. So Siberia may still have this seasonality, but it's not going to be trending so heavily because it just doesn't have all that ice from which it can be taken out of storage. So I'll tell you a little bit about our modeling efforts. This is an energy balance model approach, and it formally calculates the fluxes of sensible latent heat, solar radiation. Solar incoming radiation is the main factor that drives the melting of snow and ice at a glacier surface. There are a lot of models to do this. We're using one called Snow Model, made by Glenn Liston and others. And it has these subroutines that calculate everything from the surface energy balance, shown in this picture here, and then the redistribution of the snowpack due to wind, the interpolation of climate data. So we're using these fairly coarse gridded climate products, and we have to downscale them to an individual watershed to get better estimates at an individual location. And then the routing of the water, when we generate some melt at a given location, how does that get distributed across the landscape? And that uses a simple linear reservoir approach. So here's a picture of how that sort of works. The input to the model will be things like a land cover mask, and that's where we go back to knowing where the glaciers are located with those polygons. These are examples of the gridded climate products. We're using reanalysis data, which is kind of Are you familiar with reanalysis? It's like a weather forecast model, but applied to past conditions. So it calculates all the physics of the atmosphere, but it also assimilates in observations at the stations to give you a best estimate of the past 30 years of climate or so. And that gets fed into the model, and then we get things like an estimate of the water balance at our location of interest. So this is an animation of the kind of output we get. We're starting in the spring of 2004. And blue is where there's a net. This is a cumulative change in mass of the water. Blue is where we're getting accumulation, these high mountain areas. And you'll start to see some red emerging. That's where there's a net loss of mass. And that'll be the low elevation parts of the glaciers. So we're getting into July, and then it's going to stop here soon in August. And you'll see this is sort of a net mass balance of this entire region. Losses at low elevations, accumulation up high. And we can use that to inform a lot of our other estimates and comparisons to the GRACE data. Okay, so let's step back. I've shown you there's point, line, polygon, gridded data, multiple bands. When we look at satellite imagery, we have a vastly varying spatial and temporal resolution. So we need an infrastructure to handle that. Yeah, go ahead.
Thing. Was there anything interesting about those two inner points where there's substantial red, right on like the top left or something?
Yeah, up in here?
Yeah, those seem like the main inner points where there's substantial amounts of red. Most of the other reds are closer to the water.
Yeah, this is the Alaska range where you're right. I mean, I picked this year. This is it's a record warm year. So that was just a year where the melt extended all the way up to the top. There was very little accumulation. Those glaciers were really hit hard that year. So are you asking that with respect to what I was saying about glaciers near the ocean? Yeah. I mean, that wasn't a hard and fast rule. These interior glaciers also, they're especially susceptible to the temperature of the summer temperature, whereas here, precipitation variability can play a major role as well. So things can really fluctuate dramatically in here, but you get a really warm summer and those can be hit quite hard as well. But in terms of sea level, we're not as concerned about smaller glaciers. There's a few up in the Brooks Range as well. These are the main players because they're so large and they have potential to add a lot to the ocean. But yeah, that's a good observation. Okay, so getting into sort of the more computational part of the talk, what do we need to handle all this information? Everything I've shown you has a geospatial encoding to it. So we need to be able to do spatial querying in order to accomplish that. We need to be able to route our data iteratively. Some of our models require that we send the model output back in and do iterative model runs. Direct access to our collaborators, not just within our institute, large storage capacities and multiple processors to run these large models. So I'll go through this quickly. I wanted to outline my different sort of views of computational infrastructure that scientists tend to use. This is my version of what I think typically happens at least in my field on the academic side is a researcher will work on an individual desktop, and then typically we're using things like Python and MATLAB, Fortran code usually for the larger model simulations, generate a lot of flat files. Our raw data will be in tabular or flat file format, and then if we're lucky, that will get uploaded to some kind of national data center, and that's sort of required by a lot of our funding agencies now. And then sent out from a web server there to multiple web clients. So let me just quickly go through what I think is good and bad about this. This is a model that works okay for the individual scientist who knows where all his files are, but there are disadvantages because these flat files require us to write a lot of elaborate scripts to do any kind of spatial relationships, and it's hard for us to collaborate with each other under that model.
How is this data stored in a conventional model? Like, is it stored as in a database, or is it stored in a non-relational?
It's stored as a text file.
Oh,
literally, yeah. So it's a really not a great way to do things at all. maybe some standardized.
It's not parallel or anything. It's on one machine. How is it?
Well, it gets sent, as flat files up to a server somewhere.
Yeah, but if you have to run your whatever Python script,
Yeah.
then it's just not multi-threaded. Right?
No, it's not at all. I mean, I'm speaking in general terms here. One thing that's good about this, I think, is that the data tend to be in these national servers and labs, more stable, longer term. This is a question that came up in a talk I gave at University of Washington recently. I'll be telling you about the Azure sort of solutions that we're developing, but what happens to that in the long term? Is it as stable as something like some of these snow and ice data centers where we send our data? And they tend to have fairly good version control metadata requirements. But the main point here is that there's sort of a one-way flow of information out to the client. And if I do some reanalysis on this end or change some of the products that I'm working with, I have to go and submit it again. It might not get out to the end user as easily as I like. So this is kind of the model that in my lab I've been trying to develop, which I think is a bit of a step forward over the last couple of years. And that is, the core of it is to build a relational database for all of our work. We still write scripts to call into that and do our analysis. If we're doing any modeling, we run that off an institute computational supercomputing cluster. And then I have a local machine right in my office that is a web server in which this database lives. And then that gets served out to my institute web server and out to the community that way. So I really think relational database is fantastic for our work, and if more of us put things into this format, we would be able to advance quickly. I think this is just an example of some of the tables. Here's those detailed polygons. Here's some climate data, time series of weather stations, stream discharge, that kind of thing. We can join and relate all this information together using standardized relational queries. You probably know this really well. I'm just showing an example here of a SQL query I'll run through it very quickly. I just wanted to show quickly what you can achieve with this. This is an example of simply taking a
spatial query.
Yeah, a data. I want to know what's the average temperature in Denali National Park. That's the polygon outline for that, and very simple SQL query like that, and I can get with just a couple of lines the time series of the monthly data there. So this is really. I mean, that example is 2-kilometer grids over the state of Alaska, so it's not huge, but it's.
Like in gigabytes?
Yes, gigabyte size. Yeah. Okay. So we're using PostGIS. This is really where the functionality comes in, being able to do queries whether a geometry is contained in another geometry. And I guess, do you work with SQL Server a lot? That's something I
work with SQL.
Okay.
And, even the NoSQL, stack around Hadoop and stuff, they have similar query languages. So I
Okay.
can read this.
So I'm going to talk a bit later. I've tried to migrate over to SQL Server and investigating whether the spatial querying abilities are the same as what I have with PostGIS. And they're largely the same, but there's some differences that are making that process a little.
I don't know the specifics of the spatial query as such.
Okay, good. So this is an improvement. We can do these relational table searches. We can generate map-based products. So we're using Esri ArcGIS server to serve that out to the community right now. And one of the disadvantages of that is that we, requiring these proprietary licenses with working with those particular products. It's still kind of a one-way flow of information. One of the problems is that I become a database manager. I have to make sure I run the backups and keep the database from going down. I can't really scale it up or down based on the needs of the community or how many people are accessing it. And then if I want my colleagues to work on this, it hasn't been very successful yet. I have to teach them how to do SQL queries, make a connection to a database. It's not that difficult, but it's just haven't gotten over that barrier yet. So here at MSR, this is a summary of the kind of work that I've been doing. One is to build an API for direct access to our data, and then investigate running our hydrological models on Azure virtual machines, and then work on visualization tools and see what we can do in terms of visualizing spatial and temporal variability of what we're working on.
Right now, how does data get from your servers in the Gulf to the Azure data center?
Oh, the raw data to the well, the telemeter climate data is just using we just send a static IP address to our collaborators where the data is being generated, and it's just a scheduled script that runs, and that directly, I have a Python script that then imports that into the database directly.
So it sends it over 3G or something?
It's Iridium.
Okay.
Yeah,
Okay.
because it's out, there's no, if we had 3G, we would certainly try to use that, but most of Alaska.
That's kind of what I was wondering, like what you used to
Right.
send it.
Yeah. I just
The
want
rate at which this data is generated?
the what? Sorry.
What is the rate?
The rate. So for that particular data, it's every 2 hours we get a dump of data that has 15-minutely observations of temperature, wind speed, and so on. So that's not huge data sets there, but any other data like the radar, we would then manually ingest that into the database when we get back to the lab. It's not in real time. Yeah. This is the work for the API that I'm going to talk about next. Really is built on the previous. It's leveraging what Parker McReady did here, working on Live Ocean. And I just want to recognize that Nels and Rob really did a lot of the foundation work here. And I sort of took the Live Ocean API and just built that into what I'm calling Ice2Ocean. And this is my sort of schematic of that. And so the core of the work is this API. And we've changed things on this side a little bit. We still have this database that has all of our data. And right now it's living on an Azure virtual machine. And we're running our snow model scripts or executables also on that virtual machine. The output is sent to Azure Blob storage. And then there are calls from the API to get whatever result comes out of the model. And it's served out to multiple clients. I'm working on learning more about visualizations in Worldwide Telescope. I don't have anything to show you on that yet, but learning how to make use of those tools, and that looks very promising as well. This is just the splash page of the Ice2Ocean API. It uses a REST web service to get, in this particular case here, we're asking for a runoff grid, which is output from the snow model for a particular year, month, and day. And then the API handles things like the plot generation, file transport, reprojecting, that kind of thing. So that call would produce just, in this case, an example of a PNG that would come back through the API. And then I don't have to worry so much about this side of things. We're working with, for example, collaborators at NASA who are hoping to then make calls to the API and build them into whatever fancy web interface that they're developing. This is being put together using the Python tools for Visual Studio. The advantage here is that, again, a lot of the research community uses things like Python and MATLAB, and this has allowed me to very quickly get into this and really just take my scripts that existed and build them into the API with very little effort. So that's been great. It's using a Django web framework and gets published directly out of Visual Studio to an Azure website. Looking under the hood of the API a little bit, so a typical, one of the calls to the API is get vector. And so this would be the request coming in from the API call. And then I can just simply, like I said, cut and paste the queries that I've already written. This is that same query that I showed you earlier for the Denali data. And so my region were Denali, it would, that's the variable going into this query. And then I go to another function that's going to be called fetch polygon that I'll show you in the next slide to actually execute the query, and then the return through the API is the data set that comes out. So here's that other function called fetch polygon, and it's using a particular library that allows for connections to any standard database. This would be the connection string to that database, which, as I said, lives on the Azure virtual machine. Just set up a cursor to that connection, and then here's where you execute the query. So it's pulling the data out of the database and then returns it, and then back out the API again.
How How big is your backend? How many machines on Azure?
How big is the
Backend, like your the cluster size that you're using on Azure to store and serve all this data?
It's just a single virtual machine. I think I put 8 processors on it right now. Yeah, but I haven't really played with any of that. Nobody's really hitting this with any queries yet. It's just sort of in development, but.
Right. Is that a plan that you have, like, general public can go look at and, see various sorts of visualization of what the climate data from the Gulf looks like?
This is what we'd like to happen eventually. Yeah. That's the goal here. So I wasn't sure who would, what the audience would be, but I have some questions or things that I've investigated that I wanted to just put up here. And one is, I did investigate migrating everything to Azure SQL Server database. And we're currently still running things on the Postgres database, which, as I said earlier, this requires a lot more work on my side. So why not just put it right into an Azure database? The advantage here is really nice seamless integration with Visual Studio. The management of who can access the database is much cleaner, I think, through Azure, the web manager here. And then things like, it's redundantly backed up for me already, and there's geo-replication, and I don't have to worry about things like that. The challenges that I faced in doing this, we've had to buy a third-party software in order to do the migration, which hasn't been terribly smooth yet, and I haven't really been able to quickly spin up on that. So that just needs more time, but that's been a bit of a barrier, and that might just be related to the Postgres not talking well to SQL Server. But the other thing that I don't know much about yet is when it comes to me having to pay for these resources out of my research grants, I have to then think about the costs associated with having things on Azure. And I think there's you pay for how many queries people are hitting it with. And so those are kind of the cost benefits I'd have to consider.
Did you consider no SQL solutions at all?
So that would be using the Azure table.
Yeah, either the Azure table or something like, Hadoop or something like that. You don't really have, you probably don't need database asset semantics and stuff. So, and given, just store the data in text files as it is.
Uh-huh.
And you could, there are, Hadoop or Hadoop jobs that you can write, including in Python, Java.
Yep.
That would basically read off these, what would just be text files, put the appropriate delimiters, and calculate this. They execute the same query that you had, the group by query.
Is it as fast as something would be in the SQL
It can
Azure?
be faster because some of these cousins of Hadoop frameworks, they even allow for a lot of caching in memory.
Okay.
So it can actually be faster.
And what about geospatial searching? Find things that are within a polygon. Is that framework accommodate that?
It is something you can build on top of it, but there are lots of optimizations that otherwise exist in these kind of NoSQL solutions.
Mm-hmm.
That there might be an alternate design.
Okay, now I've heard about that, and I just haven't gone down that path, but
Okay. Yeah.
that's something I'll do for sure. I want to talk a little bit about our modeling work. Here's the way things were set up before I got started here, and that is we're working with colleagues at Oregon State University. They run the Fortran code, this snow model with all its subroutines on their cluster, and then manually upload it to our Azure Blob storage. So one step forward we've made is start to run those models on the Windows Server virtual machine, and then have a script that just automatically sends it out to blob storage, and then from blob storage through the API to the client. So what I'd ideally like to build into this in the future, and I'd welcome any ideas on how to do this well, is to actually allow the clients to request for a model run that is for a specific time and area. So give me a bounding box, and I want to, in a certain time period, so that we can then run the model according to whatever the call that's made from the client. So that would look like this, but just focusing in on that modeling side for a moment. We'd actually go to the database to pull out the gridded climate data for that bounding box in that time, send that out to multiple instances of the virtual machine based on how many calls are made, and then that goes back out again. An application of this would be, somebody living in the town of Valdez is concerned about the amount of water that's coming out of this area, potential for flooding of this little bridge that bridges this huge glacial river. So what's the discharge hydrograph going to look like for a particular time period and a particular area of interest? That's one sort of application of that idea. This is something I haven't implemented, but it's my understanding of how I would go about doing this. I learned right when I got here about the simulation runner, and it was developed here and in partnership with some other folks. And this executes parameter sweep jobs, which I think fits well to our application where we're doing multiple parallel executions of a program. And it's implemented as within the Azure Cloud Services. So I understand that the steps to do this are to create an affinity group, which is essentially a virtual network. It makes sure that all the services are in the same location for optimizing that process. The storage account stores the actual cloud service, and then it uses SQL databases to store the information on different executed jobs, and then it's deployed as an Azure Cloud Service. And you can choose a cloud service package that lists how many nodes or processors you want to be associated with that. So I haven't done this yet, but I understand that would be a good way to approach this problem. Now, the final thing that I'll show you is where we want to go a step even further with this. So I've shown you Snow Model and how it can be run over different time periods and in different spaces. Another step to add in here, remember we have all this great information from our field work that we can use to better optimize the model runs. And so I'm representing that over here in what's known as assimilation. I talked about it earlier. And that is, here's a model run shown in this first line that's uncorrected. And then, well, we know from our observations out in the field that the snowpack should have been here and should have gone away by this time. So we do an additional iterative model run that fits it back to the observations. And through that iteration, we actually get a better fit through a process of assimilation. So I think how that would look is, again, you have a call from the client for a time span and a bounding box, pulls out the data that you need from the gridded climate products, and then it also says, well, grab all of the other observations from fieldwork and other sources that also are within that bounding box and in that time period, and send that to the snow assimilation subroutine, and then do an iterative run that allows us to really improve that, and again, send that out to the blob storage location. So that's the template, I think, for the assimilation kind of approach.
Sort of correcting 20% scale errors or 100% scale errors? Or
I think typically it's on the order of 20, 30%, but I don't know if there's any limit on that. I think if you have errors that large, then it becomes a little more nonlinear, and the actual iterations might be more unstable, I think. So I think you want to be making relatively small adjustments. If you're off by 100% to begin with, then you should go back to bias correct your initial input grids. Right. So this is more kind of tweaking things to a particular basin or time period. So we're almost done here. I wanted to just say, okay, here's a future scenario a couple of years from now. Here's a couple of my colleagues out in the field. They've just taken some measurements of snow depth and some ground penetrating radar from Snow Machine. Maybe they've uploaded that to our SQL database. And then they make a call through the API for a simulation of what's the snowpack going to look like next week. And you can actually do that using weather forecast data. So instead of using historical climate products, you can generate, just like any weather forecast. That would run through the snow model. They'd come back an hour later, maybe have an app on their phone and say, okay, the snowpack's going to look like this. They can communicate with the heli skiers, and they can think about whether that's going to cause likelihood of avalanche in this area, that kind of thing. Or talk with the city of Valdez, okay, there's a likelihood of flooding this year. And that happened a couple of years ago. The whole road got washed out and things were shut down. So that's, to me, kind of the nice future model of how things could look. I think we have the capability to do something like that with some resources dedicated to that. So I'll just wrap up with a few summary points. I think these cloud resources are opening a lot of opportunities for collaborative research, real-time delivery of data to our stakeholders. Two main ways that we can improve things really quickly is more scientists using relational databases, and if we start putting our computations into virtual machines, I think that can help us get a lot of our work accomplished. And then I really like this trend of Microsoft integrating with Python and other scripting languages. This has allowed me to very quickly get up to speed, and that's what a lot of academics are using, so I think this will help greater adoption of the MSR tools. Thank you. Thanks a lot for listening. I appreciate it.
Thanks. And can you comment on scientists using relational databases? I mean, have you seen anybody go through that conversion process? And that's my first, it's a two-part question. And the second would be, supposing that everybody was, the community just kind of went off and decided they were all going to learn relational databases, how would that transform the science?
At least in my field, a lot of my colleagues don't really even speak that language. I think it's a different way of thinking. It really varies by discipline a lot, I think. So I think people in geophysics just tend to come more from just, I'm writing a Fortran program, and there's not understanding of how data can be linked together through a database. I think they don't realize they're using a relational database when they use a GIS. I mean, that's basically what that is. It's the front end on a relational database. So at least in my career, even, I don't see a lot of even just basic understanding of what could be done. When I show what we're doing, people get really excited, but they don't want to or have the time to make that extra step, because it is a big task getting everything into a standardized structure like that. But perhaps some of these other resources you've talked about could help minimize that or make that an easier step.
Yeah, just to play around, is there any sample data queries that we can get a hold of?
Sure. You mean with the data that I've been showing here?
Yeah.
Or? Yeah, absolutely. I mean,
data, so that we have. I was telling you about the thing that we're working on right now on this geo-distributed data analytics. We have a system that is going, just on top of the NoSQL, engine, and it's something. If there is some sample data and like prototypical queries, we can try to run it to see how effective.
I think that'd be great, and maybe compare, how quickly the queries run, and I'd be happy to.
Ingesting the data, these are the cooking sort of thing that you did in between, and running the actual query itself.
Yeah, let's do that. That'd be great. I have plenty of different data sets we could use, no problem. Yeah. As far as transforming, I mean, I did get a couple of my colleagues recently to really, or in particular, one of the postdocs we're working with, really adopted the Postgres and database framework. And I mean, the other co-authors on this paper were just kind of blown away with how quickly we could just investigate things. We really don't have to sit and write a huge script to do things. It's just, okay. So it really enables a quick look at our data, I think. And I think it would vastly improve our ability to collaborate and relate data together. So yeah, I mean, it's not the only answer to this problem.
No, it's just sort of like the most evolved in a sense. It's been around for the longest time. And so we see efforts at the University of Washington with eScience, with Bill Howe, working with the oceanographers to say, well, let's all learn SQL.
Right.
And that's what SQL Share was about. and variants of that theme. But, it's like you don't want to say everybody has to learn, left and right joins, but you do want everybody to sort of have an awareness of the space and what you can do with it. And to have that, aha, I get it just puts momentum behind the effort.
Yeah, I agree.
There's a kind of an intermediate stage in between using SQL directly, let's say SQL Server, and here's a query, and old school, no idea what you're talking about, which is through the type of API you're talking about. With LiveOcean and IceToOcean, you have the ability to sort of format stuff in terms of supported API queries.
Right.
It's just something you might be able to do. And then as we go through and do that, we try and build examples of an external app that generates those queries. And then there's sort of an even closer to SQL step where you say, well, I'm going to actually in my interface, my API interface, I'm going to support a grammar, which is even more difficult to program, but is potentially closer to the flexibility of SQL. So there's like this whole dial, I think, between old school flat file, write your script, and select star from. Anyway.
The API would accept SQL grammar, is that what you're saying?
Well, the example that I was talking to some other collaborators with about yesterday was with this data system that we're building for the dissolved organic matter, which is actually related to this. The discussion about queries got so complicated, they finally sort of threw up their hands and they said, we really need to create a logical grammar from which you can construct queries.
I see.
And so it's got predicates and it's got things that we're getting that are more SQL looking than just simply API calls with the main parameter and sub-qualifiers. Anyway, it's a longer discussion, but it's great to have you had it in the strength.
Yeah.
I have to push. I have a meeting at 3. Yep.
Can I get your contact information? That'd be great.
I don't have a card, but my
Here, just I have that one open.